Hello, welcome back. In this segment, I will define the discrete logarithm assumption more formally. The idea of discrete logarithm assumption is defined with the help of an experiment. Let's call that experiment d log of n. What is n? N is the size of the order of the group. Okay. Let's say you have a cyclic group G of order Q, and n denotes how many bits do you need to represent the order of the cyclic group. You can imagine n to be like the key size. Okay, of course you would like to work in a group of a large order so that it's not possible to break from a cryptographic perspective. So at this point you can imagine n as a security parameter just like the key size. Okay, first step is to run an algorithm called group generation algorithm. Let's call it gen, which takes n as the input. It will return a cyclic group G, and the order of the group is Q, and a generator G. Okay, those are the parameters it will return. Okay, and then the next step, we choose a uniform element H from the group G, randomly pick a group element. We know how to pick a group element, we saw in the previous segments. And then we have this algorithm A. What is this A that I have not explained? A, you can imagine as an adversary or an attacker. Okay, an attacker is given the group G, the order of the group is Q, and a group generator small g, and the uniformly picked element H. So what is the purpose of the attacker? The purpose of the attacker is to output an element X from the group ZQ. If he is able to successfully come up with an X such that G power X is equal to H, then the experiment will return 1. Otherwise, the experiment will return 0. Okay, so essentially you are asking an attacker, assume like this visually, you have an attacker A, you say to the attacker, try to break discrete logarithm problem. Essentially you're saying, you send in, here is my group that I'm working with, right? It could be Z star P or whatever, and here is my group generator, and here is the order of the group. Okay, and I give you a randomly picked group element H, and your goal is to give me back an X. Okay, he may or may not be able to come up with an X. The X he is going to give should satisfy this property. If he is able to come up with such an X, then we know we are in deep trouble from a cryptographic perspective. You will see later when I talk about Diffie-Hellman why we don't want this to happen. Okay, if an attacker is able to come up with an X, the discrete logarithm experiment will return 1, otherwise it returns 0. Okay, this is how we defined the discrete logarithm experiment more precisely, formally. All right, now let's get back and define the notion of the discrete logarithm hardness. Okay, what do we mean by discrete logarithm hardness from a computational perspective? Let me formally define that. So the idea is that for all possible adversary A, or for all possible algorithm A, the probability that d log, right, returns 1 is bounded by a negligible function of n. Remember, n stands for the size of the order of the group. Okay, we believe this is true. Otherwise, Diffie-Hellman key exchange and all other algorithms based on discrete logarithm are not secure. Okay, so this is an assumption. Okay, we don't know whether this is true or not. This is an assumption. So for all possible adversary A, okay, or algorithm, whatever smart algorithm that you could come up with, you feed in a security parameter. That algorithm returning 1 should be negligible in n. Okay, that's basically that the probability that the algorithm returns 1 should be negligible in n, which means the algorithm will most likely return 0 all the time. It was not able to come up with an X such that G power X is equal to H. Remember, this is a one-to-one function. Given a G and a H, there is only one X. Okay, and the goal is to find such an X. All right, that's basically the definition of discrete logarithm assumption. All right, that's all. Thank you very much for your attention.